thanks everyone for coming out. I don't know what number this is. Which number is it? 10? All right, so 10th edition of Papers We Love Toronto. We have Ben Darwin here talking to us about algebraic effects and handlers. And thank you all for coming. Take it away, Ben.
Thanks. So what I want to do tonight is not sort of follow this paper in a very linear way, because it's quite hard to read that way, and also I don't think it's that beneficial to spend a lot of time staring at type derivations, and especially the denotational semantics, which is be a bit difficult to explain in the time we have, and I don't understand all of it so well myself. So instead, I want to start by trying to motivate why we care about these things, why they're interesting, and how they're all kind of obvious from things that you already know about, at least if you have encountered some modern programming language and aren't like a C programmer or something. So why do you care? As we all know, software engineering is about managing complexity. Programs must be written for people to read, as they say. We'll also see that compiler writers, library writers are interested in these things for kind of performance purposes, but for us, they're interesting as a programming API. Specifically, one particular place where they're useful is testing and formal verification. We'll see that it's quite a useful thing. They can help you with some kind of things that are otherwise awkward to test. So what are effects? Basically, the idea of effect analysis. In some way, we want to talk about, compute, restrict, what kinds of things a program can do. So basically, anything other than kind of returning a value. But even returning a value, well, without effects, it'll never be printed at the screen. So typical examples: termination, calling a specific function, raising exceptions, reading from a file. So all the things that make programs useful. Some of them are questionable. So I mean, non-termination, widely accepted as an effect, but heating the CPU, I mean, you have to set your abstraction boundaries somewhere. So this looks a bit like types, where we say what values can a function return. Here we're saying what other things other than returning a value can it do, and indeed there's a book on programming language analysis that classifies types and effects together as one of the four main types of program analyses, and probably one of the most interesting from the programmer perspective as opposed to a compiler writer perspective. Some languages already have sort of effects encoded in types. We'll see a little bit of Haskell later. Many languages are typed, say Scala or even C. Then you have dynamically typed languages like Ruby or Python, which the types are implicit, not explicit, but having the types explicit gives you many optimizations and the ability to say certain things about your programs. Effects more than types have historically not been available in that way. I mean, GCC or the JVM knows a lot about your program that you don't know, but you don't have access to that way of talking about your program other than in an informal way. So algebraic effect is one way of trying to bring that power to the programming language itself. So I guess the story sort of begins around the late 80s, early 90s. People were studying programming languages from they were trying to give mathematical meaning to programming languages. Specifically, in '91, there was a famous paper by Eugenio Moggi, I hope I'm pronouncing his name right, and he used a category theoretic construct called monads to understand non-functional features like state and so on in a programming language. And then Philip Wadler came along shortly afterwards, and he realized, well, these monads are great, why don't we add them to the language itself? So instead of just analyzing the language in terms of monads, let's give them to the programmer. And this is how effects are managed through a monadic interface in Haskell today. The algebraic approach started a bit later. Some of the influential papers are these Plotkin and Power papers in the early 2000s. And then Plotkin and Pretnar collaborated on this paper in 2009, and then this paper is from 2012. So it's also a kind of mathematical approach to study of languages that kind of got imported from the meta theory into the language itself. So very trivial example, if you had programs with result types v, and then you would add a kind of exception effect by saying, well, the result of this program could be one of these values v, or it could be the disjoint union with some other exception type e. And so this is something similar to monads that has come into programming languages. It's kind of fully subsumed by monads. The monadic approach is actually more general. But it's interesting anyway because maybe it's a little bit lighter weight. It's somewhere in between kind of unrestricted effects like in JavaScript and effect types like in Haskell. So let's just kind of look at the problem from the kind of more strongly typed side. So in Haskell, we can define an action type, and this action encodes, so an action is a program fragment that has an integer state, and it might throw a certain exception I've defined here, and it also might do I/O. So the first thing we can see is our types are kind of ballooning, and then we also have to define some way of getting a program, something that actually runs out of this action. So the types become larger, and then we also have to kind of compose all these evaluation or running procedures. And then you can write an action which has this action type, and it can do things like get from the state, which you have to you have to supply the state with the eval state. So you kind of inject that state. You can do I/O, and you can modify the state, and you can throw exceptions. So, but like I said, this is a bit tedious. You have to call these run functions explicitly. Your types become kind of large. And sometimes you have this big stack of effects, exceptions, logging, I/O, and so on. And it's very big, and maybe you only actually care about one or two of those effects at a certain point in your analysis or development. So that was sort of the motivation for the algebraic effects side. And what this paper has done is kind of moved combined handlers into the algebraic approach. So the obvious generalization here is an exception handler, but I want to try to kind of motivate this a little bit. So there's kind of some odd similarities between many of these different effects, and maybe they all have a common unified way of thinking about them. So is this a good C program? It's just going to print all the integers. All the non-negative integers. So some people are saying, sure, maybe it is. I haven't told you how it's going to be used, right? So you cannot really say. Is this a good C program if I'm going to call it from another C function? Probably not, because it's just going to kind of go on its own thing and never return. What if this were a shell script? Then everything's fine, because I can just call my bash take10 or head or tail. But I can use part of it, and it will be suspended. Like bash is controlling the standard output that this is printing to, so it will suspend after it fills up whatever queue or like whatever it's writing to. So it's fine as a Unix utility, maybe not so good as a C library function. Is this good Python? This is exactly the same thing, except it's yielding. So somehow all I did was change yield and print here. But this function can be used inside Python perfectly easily. Other Python procedures play happily with it. So somehow the dynamic context matters. When the shell was managing the output that I was printing to and stopping my execution, then that became useful. And that's basically what the Python example is doing. So somehow the dynamic context that we're evaluating inside matters. In the bash case, you can think of the C program definitely has this effect of print, but if I'm a shell user, I can pipe that to dev null. I sort of remove this one effect from that C procedure. So another example, so this is a kind of very intuitive, and you shouldn't take anything that I'm saying at this point too seriously. But another example is the similarity between state and exceptions. So both form monads. In Haskell, this is explicitly part of their API. They both have a monadic API. And in fact, there's a deep categorical duality behind this. I guess the obvious way that it manifests in programming is if I start setting the state of the same variable more than once, it's the last one that matters. Whereas if I start throwing the same exception repeatedly, it's only the first one. And the rest is discarded. So Java also tried to tame effects a little bit. So in Haskell, my Haskell example, I said, well, this function might throw effects or it might not throw effects at all. In Java, they tried to figure out, can we restrict which effects might be thrown? So here's a method that is declared to throw a certain exception, and then anyone that calls this method must either add this throw some exception to their signature or catch it and do something else. But it's unwieldy. It's not very popular, or at least very controversial in the Java world, from what I understand. And somehow, if you were forced to do this with all your exceptions, which is what you kind of want for safety, or the kind of safety that this API is attempting, then you have to start leaking things like division by 0 and from functions that you don't care if they're doing arithmetic. And so somehow it's not modular. You leak implementation details if you adhere to this discipline too strictly. So there's some common Lisp programmers in the room, and I asked them about this, and they told me that most people don't actually use this feature. But Common Lisp has an interesting feature of its conditions, restarts, and handlers. So I didn't put the Common Lisp code up, but I guess a typical example is, well, something that I was doing today. If you're writing some parser that parses some kind of file, doesn't matter, a log file or a configuration file or something, you might come up on the situation where the low-level parsing function, you think to yourself, well, I should print a warning at this point, or I should throw an exception, or I should do something, but because some value is missing or malformed or something, but it's not clear that this is always an error. So maybe someone else can supply that value for you. And what Common Lisp lets you do is, instead of throwing an exception, you signal a condition, you offer to the high-level handler, you say, well, I have these following restarts. Provide one of them is the user can enter a value at the command line. Another one is you can write to some other log, or I can restart. I can parse this as an empty log file or something, and then the low-level parser function will be restarted where it left off with this state kind of fixed. So the idea here is don't discard the remainder of the computation, which is what an exception does. It just kind of bails out and unwinds the stack. So, I mean, this has all been kind of intuitive, but the three key ideas on the kind of handler side of things are start with exceptions, but also pass the continuation along and let the user, the code handling the effect that or the condition that gets signaled, decide what to do. So this is basically, I basically told you how the effect system is going to work. I just want to, as an aside, probably many people are familiar with continuations and some aren't, but the idea is if we're evaluating at some point in the computation, such as when we're adding 3 to 4, we haven't performed this addition yet and we haven't performed the square root because this wasn't done. So we have, after we add 3 and 4 together to get 7, we somehow have to remember which operation was done by the stack, but that doesn't really matter. Remember the remainder of the computation. So we can represent where we are as in some abstract sense as maybe box is our current position, and then this is the remainder of the work that has to be done. If this is an abstract representation of a continuation, we'd also like to choose a concrete representation so we can give it to the programmer. Well, and if you're a closure programmer or a Scala programmer that has kind of special syntax for one-argument functions, then you know we're already there. Otherwise, well, it's clearly the good concrete representation is a callback. So here, let the continuation k be the function that receives a value 7 in this case, and then returns this result. So that's all that a continuation is. It's a callback, I guess, representing our current location in the code. You can also have a delimited continuation, which doesn't capture the control all the way up to the top level of the program, but it's trapped by some other enclosing statement. So with that in mind, I just want to give you a little bit of a taste of what F looks like, because so that you won't be, so your eyes can adjust basically. It looks like this. So this is the map function. Let rec says I'm declaring a recursive function. Map, it's 2 arguments. The function to apply, the list to apply it to, pattern matching. Don't use this version because it's not tail recursive and so on. But then the evaluator says, well, map has this type, so A and B are type variables. So it says if your function takes an A to a B and you give me an A list, I'll give you a B list as a result. Well, looks like OCaml, and that's because this is OCaml. F is implemented in OCaml, and the syntax is basically the same, except F has fewer features and some more features. So instead of going through like I said, instead of going through the paper and telling you these are the constructs specially added to F and how they work, I'm just going to start with an example and show you the cool things that you can do. So the first example is non-deterministic choice. What is non-deterministic choice? It's some construct in my program that returns randomly or according to some specific way, but it somehow returns multiple results. So the first thing that you can do in the F language is declare a new effect called choice, and you attach to it one operation symbol called decide. Decide is unit to bool, so it's going to, you just call it with no arguments and it says yes or no. So you can create instances using new, which looks a little bit like object-oriented programming and kind of similar in the sense that you can think of this sharp symbol as, well, this is the selecting out the operation symbol of decide operation symbol on C. So this whole thing is then called an operation, or but it's, I guess, not like object-oriented programming, because although this does kind of look like a message send, normal control flow is kind of altered in some way when such a message is created. So C# decide is just an operation, and it's kind of harmless. It's a value. You can pass it around, but as soon as you've applied it to its argument, and all of these operation symbols take only one argument, but you can always give it a tuple or a list, so it doesn't matter. Then this thing is now computation, and it's like you've called raise exception in Python or Ruby, and it's now doing its own thing. So if we write a computation using C# decide, say let x be a non-deterministic choice of 10 or 20, y be a non-deterministic choice of 0 or 5, and then take the difference. Well, this computation obviously can't execute because we didn't specify any meaning of C decide. It's kind of it's just an algebraic symbol that doesn't have any intrinsic meaning. And so we give meaning by handlers. So here we handle the computation from the previous slide, and we say, well, when you encounter this symbol and its argument and the continuation, call the continuation with the result true. So you're filling in the rest of the computation with true. So the answer is 10, and let's see why. So control starts executing, let x equal, this computation is run, we start searching upwards for the nearest enclosing handler. The handler gets the operation with its arguments and the current continuation. Now the current continuation is the whole rest of this with just a hole here. And then we say do the rest of the computation with true filled in. So it's effectively, we replace C decide unit with true, and then so let x equal, if true then 10, so this is now 10. Continue executing with x being 10. Same thing for y. Control bounces out to the handler. We say continue with true here, so then you get 10 and 0, and the answer is 10. So the interesting thing here is that, of course, there's more than one way to handle such computation. Here we said, well, the answer is always true, but so it could also be false or it could be random. This is just what the computation, the continuations look like from the previous slide. We can define a handler separately from the use site. So instead of saying handle with, and then this kind of pattern matching, we can say let H be the following handler that has only one clause. And then we can say with that handler, handle whatever computation. So there's two kind of equivalent syntaxes. So another handler we can write is, instead of just always using true or false or choosing randomly, or we can accumulate all effects. So here, when we encounter, so first of all, we generalized over the specific choice of choice effect in the program, and we said choose all given a choice. Well, when an operation, decide operation is raised with the continuation, call the continuation with the result true. So that gives the whole answer of 10 that we got last time. Now call it with false. And this will give a result or some other results. But now there's a trick, so we enclose each one in a list, and now this is append. So we accumulate all results from all possible choices of true and false. So what the so there's an additional clause in the handler, which is val x goes to x. And what this says is, if control returns to the handler, the computation finishes, bind x to the whole finished thing and return this instead of what you were going to return. So that just takes the 10 from the first true case and turns it into the list 10 so that it can be appended to the list, true, false, false, true, false, false. And then handling the same computation gives a list of these results. So we deferred a choice of which kind of what kind of non-determinism we were really talking about by saying, well, just write your program with these abstract algebraic symbols, and later you can decide what they mean. So why do we have multiple instances of choice? So we had C, but we can say, let C1 be a new choice and C2 be a new choice effect in the program. And now this is different from the previous program where we just had one and the computation was the same, and my formatting is wrong. But if you trace through this program, this effect is raised to this handler, which restarts this whole thing. So now there's some non-determinism inside non-determinism, and we get a nested list of lists of the results. And there's various things you can do in the paper. They give you more examples, so they flip these things around, and you can get doubly nested lists in other orders or various things. But basically, everything is going by the same principle of every time you encounter an operation, an effect in computation, you go out to the nearest enclosing handler of that operation, and it dispatches the continuation in the way that it wants. Another alternative would be we could handle C1 with accumulate all effects, and C2 just choose one, depending on what we want on that particular day or for a particular purpose. This was an obvious example. Exceptions. So I declare an exception, a class of affection types, exception types. So there's a type variable, and you can raise a value of some type A. Empty is the type that's uninhabited because raising an exception, well, control will never return to that point in the program. Let E be a new exception, and then, so what happens if I run this function that checks if something's a negative number in this handler, and then catch an exception and just return the raised value? So it seems obvious that this should just give us bad, but actually gives us a type error. And that's just because we said raise returns the empty type. So what we have to do is define this silly function that matches against the empty type and gives you a value of the type you want back. And then we can have raise just as we do in normal programming languages, and this will work correctly. And the else good is missing, but it will raise, that doesn't matter because it'll raise bad. So how does this compare to exceptions in other languages? Exceptions in Python or SML or other languages are extensible, so you can just say class exception or declare a new exception on you whenever you want, and then pattern match against that specific type. In F, it doesn't have that, but it's just because the authors didn't bother adding it. You can all catch, any exceptions in other languages can be caught by the same handler. You can always say except E or catch everything. But this is just like if in F you only had one new exception E. You said let E equals new exception in your program, and then you never said new exception again. So in F, you could always create a new exception kind of locally, and then nobody else would be able to catch that. And you could pass it around, and only people that you gave it to would be able to even catch that exception at all. I don't know how useful it is, but some people are fans of Rob Harper's blog, and he says exceptions are shared secrets. So this is one way in which F exceptions are more secretive, or scoped if you want. So another example, of course, is I/O. So let's define a channel to be an effect that you can read and write on. Standard channel. So in F, standard is kind of a magic channel because it actually does things. But for in general, we can use these channels inside our program and kind of eliminate them in the same way that we did with the C program when we were Bash users. And you can sort of do that in some programming languages. You can redirect standard out or something, but you need some kind of dynamic handling, otherwise maybe you forget to change it back when control leaves whatever block you're in or something. So we can define, obviously, dev null to be the handler, well, only for the standard channel. Whenever you send me a value, I just say, well, you're replaced with the value nil, continue the rest of the computation. So the next two are pretty useful for testing because you can use them to introduce or eliminate I/O effects. So accumulate collects a bunch of writes to this channel, and accumulate returns the value together with all the effects that it found. The continuation stuff looks kind of weird, but it's all sort of obvious if you trace through, just in the same way that control flows from a raised condition up to a handler and then back down with the handler receiving the continuation. Read from a list is the opposite, of course. So it takes a list of things and gives you some, accumulate catches I/O operations and turns them into a list. List, read from list, turns a read operation into so how does this work? This one is quite mysterious, and I have 3 question marks because the continuation has 2 arguments, and how does that work? And the return from signaling this condition never invokes the continuation again directly, Instead, it creates a new closure. So what's going on here, you supply a list, calls to read, build up a chain of functions, and then finally, so val, once the computation exits, you create a constant function that returns the value that the handler got. Finally, so this is kind of the trick here, finally executes after everything here is finished. So we've built up a function from this whole block without the finally clause. We now call it on this input list, and it's a function that takes list elements and invokes the continuation on the first one and then the remainder. But the other trick was we didn't call the continuation here, so we never returned to the computation. So how did the read calls actually happen? What happens is this function is built, or some function is built, finally happens, function is called, the function calls the continuation inside it. So the first time someone calls read, we leave this computation completely. And then we run the finally. And finally calls the continuation inside it. So we go back in, and we go to the next read. And then we call the continuation with the result of the second read, and so on. So control flow in this example is very bizarre, and it's not obvious. I mean, it wasn't obvious to me why this works, but the type of because of the way that we're entering and re-entering the computation, the continuation it takes these two arguments because of the result type, the fact that we're returning functions here. I mean, you could say this must be true by type correctness, and that there's probably only one way to write this. So this is a cool trick, and read from list is a very nice thing to use in your program because you could say, well, I'm mocking out my network or whatever. But I guess the control flow inside here is getting a little bit strange. Another example that uses exactly the same trick of returning functions, and then the continuation accepts two arguments, state. So what can you do with a state variable? You can look up the value and update it with a new value. These are kind of the obvious things that if you sit down with your type checker, it'll tell you you must write this. Return a constant function again. And so you find, again, this computation builds up a function, and then you finally call it on the initial state that you supply. It's like, this state reference is going to have this initial state. So it's a little bit like Haskell, where you had the choice of injecting whatever initial state you wanted into this part of the computation. So it's a little bit verbose to write the state handling this way, but the biggest problem is the reference may escape all its handlers. Say if you wrap it in a closure and pass it out of a function, then any lookup or update operations, they propagate up to the top level of the program, and your program crashes. So this isn't quite the right behavior for references, immutable references, to have. So this is kind of, when I first read this, it seemed a little bit underhanded. We introduced some new feature to the language to fix this problem. And specifically, the feature they introduced looks a little bit like state itself. So I was a bit disappointed by that. But it turns out this is kind of the same thing that has happened historically in Haskell, where monadic features were moved into the program. This feature called resources is inspired by, I guess, co-algebraic semantics, which I can't really tell you much about. But the idea is you can declare after a new, you can put this @ sign, which is no longer list append, but it's some kind of tupling operation, and you declare X is going to be the initial resource state of this reference, and then you your lookup type, your operation types, so they now take this too. S gets the value on this side of the current resource state, and your contract changes, so you must return a tuple. The first component is what goes to the continuation. The second component becomes the new state of the new effect that you created. So I was like, well, this is just state. How can you implement mutable references in your language and say, now we've implemented state? And it's true, I guess the mutable reference example isn't that magical anymore, but just like in Haskell, you always had this theory outside your language that could be used to implement state. You could transform your language somehow and get state in it, and this is just what's happening. But because this is kind of mathematically informed, it turns out to be, I guess, a kind of nice abstraction versus maybe in Python, say, where you added some construct to the language, and it really expands into something this long. If you look at the Python enhancement proposal, it's like calling all these kind of methods, and you're like, well, are the corner cases here really safe? It seems like this is a relatively simple and straightforward thing to do, and it provides various benefits. There's a couple other examples that use it, I think. They use a magical reference that has, I guess, runtime support to implement the standard channels. This is a cool example. So maybe 50 years from now, some new programming language will be released and it'll have transactional support. I mean, a couple languages have that now, Haskell and Clojure. So maybe 50 years from now, like something will come up from Google and it'll be like, oh, does your language have transactions? And you say, well, we had that in 2012. Anyway, so these are syntactic sugar functions for SML style. So you use a assignment equals to set variables and a bang to dereference them. So a transaction, again, the same trick. Don't call the continuation immediately, but build up some nested function. Only when you get to the top of the handler and the val case is invoked, set the reference. So you committed, and then return the result. So unhandled raise operation here will come up to this transaction R handler doesn't handle E, so control leaves this. And because the val clause is never invoked, well, this last is it's never seen, but this is one of my favorite examples, cooperative multithreading. Well, what's the API for cooperative multithreading? So these threads are symmetric and not like yielding one thread yields specifically a value to another thread. The thread will just call this yield operation and say, I'm finished right now. And then a thread can also spawn another thread, which is looks like a unit-to-unit function. And again, we have the choice of how to interpret this kind of thing. So whatever handler we create for cooperative effects will determine our scheduling strategy. So here's one scheduler, a round-robin scheduler. What I like about this example is that you can implement this in other ways if you have continuations or delimited continuations or various other things in your language. But this one it's fairly obvious. It's sort of the most obvious thing you can do. So we set up some variables for threads, a thread pool, I guess, NQ and DQ operations. So what this is it sets threads to be the current value of threads, appending whatever thread you ask to enqueue. DQ pattern match on the current contents of the thread variable. If it's empty, just return nil. If it's a list, set the thread variable to the remainder of the list, and then immediately start. So this is DQ immediately starts running the thread that it pops. So then the scheduler itself is a handler, and it handles a yield operation by queuing the old continuation, and then which is the processor thread, and then starting a new one. Forking, well, the same thing. Put the old record onto the stack, and then handle. So we need to handle the execution of the new thread with the same scheduler, because otherwise, if we didn't have this with scheduler and so on, handle here, this would kind of escape. Call to T would escape the handler, and then finally there's no result, and then recursively call yourself. So any questions so far? I guess we've covered a bunch of the cool examples, but at any time, just like throw up your hand or whatever, or shout at me, fruit, it's all good. Yeah.
Can you go back to the last slide? So, is it the case that I'm able to follow like a substantial part of this, but one thing I don't quite get is like in this language you need to be, anytime you do effects, you need to be writing these handlers, and that's the only place where you can actually describe the effects, right?
So, right, F is sort of a pure language, like Haskell or something, that has had effects added to it as the way of doing non-pure things.
So, in this example, let's say, what are the things that go on in the handler that, like, where are the points in this code that deviate from the pure language and actually do the...
So in this code, there's nothing, because we didn't write any threads. So to write a thread, you write a function from unit to unit. And that function can print and read and do what it wants, but it can also call these other operations, yield and fork. That's the impure part. This handler has some effect handling stuff in it, but it's sort of pure because it itself doesn't really do anything. It just receives the continuation from threads that are just these functions that call yield and fork.
So all the code that you write is actually pure. But
Well, if you wrote a thread that called yield, that's sort of impure because control leaves that that function is executing purely. Well, I mean, it's also unit to unit, so it can't do anything. It can't return a result.
Right.
So it's going to somehow print or something, which is going to be impure. But then it will also call fork, and that's going to cause control to suddenly leave that function. And now control leaving that function is impure because.
yeah. So it's basically like any of these. Well, is it the case that like any of these times when you're calling a function with unit as the argument that like are all of those like impure, like they are done for side effects?
Right. Anytime you write something, so you can think of this handler as maybe sort of pure, but anytime you were writing something like this, not inside a handler, but inside code that you want to be handled later, that's an impure operation right there.
Right.
So anytime you see that sharp sign applied to an argument, yeah, that's exactly when the impure action is happening.
Right.
So there's a few more examples in the paper. How much time? What time is it?
About 44 minutes in.
So these examples are a bit longer. So there's some more nondeterminism, which is similar to the first example of the choose function, but a little bit more involved. I guess the lesson here in the paper is that sometimes it's not quite obvious. In some ways, this is a nicer style than programming with maybe delimited continuations directly, but reordering the handlers it can be hard to understand the way in which things are interacting sometimes. You can also add, so we had state and transactions. You can also add a lazy references that kind of are thunks and updated once you look at them. So this isn't in the paper at all, but since I used restart as a motivating example, here's one proposal on what you can do to implement restarts in F. So you raise an exception, but with your exception, you include a table of options of what the handling function can do. You say, here's a dictionary, and maybe one entry is user value, and so the low-level function supplies a function that you call, and when you call that function, it parses its stuff with your supplied value, filling in the empty field. And then you call the continuation on that and keep going. So somehow this seems to subsume common Lisp restarts. You might need some better syntax. I haven't tried, so I don't know if you could define some functions for restarts, or if this would be one of these things. You can do it, but the syntax is too complicated and no one uses it. And then 5 years later, someone writes a macro or comes up with a completely new programming language just to change this one syntactic detail. And I'm not sure exactly what the common Lisp semantics are, so I don't know if you could replicate it exactly. They're probably pretty complicated, though. So I just want to explain a couple things that were kind of like informally hand-waved about the language, just so that maybe you can understand the examples more in better detail if you study them more deeply at some point. So, like I said, I kind of hinted this, there's expressions and computations. Expressions are pure values, and the computations may cause an effect, including divergence. So the expressions are things like variables. A variable refers to something that's already been computed, so it's not dangerous. Same with a number, or a constant, or true or false unit, or a pair of expressions. Because they've already been computed, they're not dangerous either. Left and right, you'll recognize these from Scala or Haskell. Closures, operation symbols, and handlers are all safe expressions. But all of these things, as soon as they have computations in them, they become dangerous. So one interesting thing that you notice is that an expression, E here is an expression, so val E, expressions are also computations when you wrap them in val. But F actually wraps them in val for you, so you could mostly ignore that detail and program with things regardless of whether they might be affecting or not. You don't have to worry about it. Well, what if you put so it's fine to put an expression in a computation position because that's harmless. But what if you put a computation in an expression position? So what happens then is there's a desugaring, and it says, let a new variable x equal the result of your computation in x. So this is just a kind of general case of the handler that we've seen all the time. Handlers handling one or more operation symbols. So with an argument and with the continuation, and then a val and a finally clause, and then they're handled with H handle C or handle C with H. Without the finally clause, if you evaluate to val, the result is CV with X bound to E. So this is just formalizing the kind of obvious things. The val case is not very interesting. If evaluation of C encounters a raised operation, it evaluates to the appropriate clause in the handler with the value and continuation bound to the obvious things. The interesting thing is the continuation K that you get in the handler clause is delimited by the same with statement as the original as the original C and handled by H. So the continuation is sort of, once it starts running, it's already inside this handler. And that's why all of our examples where we kind of bounce back and forth between the continuation and some function that we built up worked. If they were outside this, then we would just get an exception when we tried this. If you add a finally clause, then that's like saying let x be with the thing without the handler with the finally clause removed, bind the result of that to a variable, and then evaluate the thing after the finally with x bound to this result. So this is kind of the obvious thing again, but it's just kind of the reason why the intuitive examples actually sort of worked. So is this this is cool, right? Like, I think so, maybe. What's bad about it? So, like I said, the monadic approach to effects is actually more general. It kind of encompasses this one. The hope is that this one is easier to use, or in some sense lighter weight, maybe. So transformers give you more guarantees and better equational reasoning. So the interactions between handlers can be hard to understand. We didn't really see that too much, but in some of the longer examples in the paper, like I said, interchanging the order of handlers and effects can be confusing to understand. And that maybe that's the same issue. Maybe the fact that the theory is not as good. Maybe that's the same problem. This hard to understand part is because the underlying theory is not as good. I can't really say, but another problem, it doesn't work so well in lazy languages. I can't really speak to that one very much, but, well, it cannot, like I said, it can't encompass all monad transformers. There's a kind of very crazy and lengthy critique of effects versus monad transformers that was posted by Ed Kmet, who's kind of one of the premier Haskell programmers. And it's very dense, and I understand very little of it. Go ahead.
I know you said you can't speak to don't work well, but what is the idea that you're trying to convey with don't work well in lazy languages? What is the definition of well there, or what does it mean to work well in lazy languages?
So, for instance, a lazy writer monad or a lazy reader, which are kind of like logging and printing. Well, a writer is like logging, and a reader is like is some kind of context injection. You can't implement them using these. That's part of this not as general issue, but also there are kind of asymptotic efficiency issues. If I implement these things as kind of libraries, like the examples, in a lazy language, you sometimes run into problems with asymptotics, so it's hard to implement them efficiently.
But isn't that just something part and parcel of the fact that you're in a lazy language?
Right.
Right. I mean, so but that's not about the technique of algebraic handlers per se.
It's a limitation because you can't use them in that setting. So I mean,
But that's like you can't do anything like as in a lazy language. No matter what you're doing, it's hard to in a lazy language where you don't have types or some other thing which is allowing you to enforce or be able to track what are the asymptotics. And I don't know of any language which does that, which is also lazy. So short of that, it's hard to actually write code where you don't mess up the asymptotics. So I think that's a given. Whether you use any effect library or effect system or not, or even if you're just writing any pure computation code, right? That's just an artifact of current implementations of lazy languages because I don't know of any which allows you to track asymptotics.
So, right. So I guess from what I understand, the problem isn't so much it's hard to reason about the asymptotics because, I mean, that's kind of a general problem in lazy languages. But there are some effects that you would like to write, but it's just nobody knows how to write them in an efficient way.
So Andrej Kmet's the example that he gives, and that's pretty that encompasses. So in you can do most of the things that you want to do with lazy extensible, like the algebraic handlers can be used to model the closed setting as well as the open setting. But it's more about the open or closed setting. If you are in the open setting and that's the default, which I believe the algebraic handlers approach take, I think F does that as well. I'm not sure. I haven't actually used the language. I know that extensible effects use that. I know handlers in action tries to do that or have the open setting. So that's more about the open versus closed.
But it's still, right, I see what you're saying, but it still seems that if the situation of transformers versus effects is worse in the lazy setting, then all I'm saying is that if you're in a lazy setting,
That's my point. It isn't worse in a lazy setting. Laziness has nothing to do with it.
So, but it's not easy to implement lazy reader and lazy writer and so on in this model. So,
Well, but it is possible. So
Okay.
there's a code example on the GitHub for extensible effects. This was like communication with Oleg, who was the
Okay.
author of that. And there's a new version of the library which makes that update, moving away from the free monad construct to a quote-unquote freer monad,
Okay.
which fixes that issue. So it's more about the implementation as opposed to the idea of algebraic handlers.
okay, so I don't know how much of that got recorded, but the maintainer of Haskell extensible effects slightly disputes that they don't work well in lazy languages and says that some of these problems with lazy reader and lazy write and so on have been solved by proposing, I guess, new implementations. So what other related work is there? So this was kind of one of the first papers on the F language, but you can also start F with this -- effects flag, and then it will infer effects for you. So we had this map example earlier, and that wasn't completely random. The purpose was, well, now map, if you ask it for its type with this flag, you'll say it's now a function from A to B to an A list to a B list, but now the function arrows have been annotated. So if F, the function that map is calling on the arguments, can produce effects D, then map is now also contaminated with those effects D. And it uses row polymorphism, which is kind of an alternative to subtyping, to talking about, I hesitate to say extensible collections, but what it does is it gives us better type inference than subtyping, and it lets us talk about only the effects that we care about. So we can say, my handler takes a function that might print and might have other effects and removes the ability to print. And that can be inferred. So we can kind of have, it's not really discussed in this paper, it's discussed in the follow-up paper, inferring algebraic effects. But we can have, we can take things that look just like our ordinary programs and then say, well, this one does perform a certain effect, this one does not perform a certain effect. And that's kind of what you wanted. So there's another paper later in 2012 from I think Microsoft Research on the Coca language, which is also uses effects. And then based on I think this paper, Haskell has these extensible effects and another what's the library called?
Handlers in action, I believe.
Handlers in action.
From that paper.
Oh, okay. From the Handlers in Action paper. Idris' effect system is also built around this F star as another experimental language, which combines this feature with kind of more advanced type system features. And finally, OCaml Multicore recently got one branch of OCaml Labs repository has recently added these effects for, I guess, thread scheduling. But in principle, the same ideas should work. OCaml already has row polymorphism for its object system. I don't know if they're using it yet for these. I'm not sure. So it's a convenient tool. It allows high-level code to change the meaning of low-level code. In some ways, it's lighter weight than programming directly with monads or delimiting continuations or callbacks. And you can also infer the effects. They compose relatively easily, but sometimes there's some question about what the meaning of the composed thing is in terms of it may not satisfy certain laws or may not, your equational reasoning capacity is limited. That's all.
I had a couple of questions. In Haskell, for instance, in the I/O method, you would push the I/O computation to your main entry point main, and then the runtime system, when you execute your program, will execute your I/O computation. So if this were if F is a pure language, would there be some sort of implicit top-level handler for I/O that will always be in scope or something?
Right, for sure. I mean, there's no I/O effect. It's split into, say, a printing effect, and I mean, it's broken up. You could define. I mean, you can imagine having separate effects for like networking or whatever, which I guess is not really a limitation of Haskell approach, but just like the effect types that were defined for it. But of course, right. So there's this standard. There's a channel standard that's defined, and its resource. It has this associated resource, which has runtime magic in it, which. Right, so an unhandled call to standard read goes up to the top level, and then, yes. So, right, I guess there's some implicit top level magic handlers. I guess you give up some equational reasoning because you can't say, well, these things are actually actions. Like in Haskell, you say something of type IO, whatever, is actually an action, and I can substitute it freely in the program because it's never called. But I guess you would sort of do that with a operation symbol before you apply to its argument. I'm not sure what the equational theory looks like, actually. And they say sort of near the end of the paper, this is also something we're investigating.
And then the second question is just that I noticed at the very beginning, you got a runtime error when the effect wasn't handled.
Right.
And I'm not familiar with the theory side of it, but I'm wondering, with the exception of exceptions, I would think that you would want to get a compilation error if you didn't handle an effect. Whereas maybe with exceptions, you would want them to be runtime exceptions. But all the other kinds, I would think that you wouldn't want it to be a runtime because then you could write arbitrary code with tons of effects and you wouldn't necessarily know that you've handled all of them.
Right.
So what are your thoughts? Is there something that ensures, is this a problem that you could potentially have all these runtime problems? And if it is, I think that's significant.
Right, so the question is it bad that many different things that aren't exception can propagate up to the top level? There was one example, I guess, early on with choice or something like that, where we let it intentionally propagate up and we got a runtime error. And the question is it good to have this potentially many things that may reach the top level in our program?
Is it possible that you could
Can you eliminate
make
it?
a compilation error that you haven't handled this effect somewhere?
Can you make it a compilation? So I'm not sure. I don't know. Using this polymorphism, maybe you could say, well, my main function can only have certain effects. Yeah, I'm not certain. All right. Good night.